Well, surprise, surprise, technical issues. First recording. So, I just look strange. It's because I've chopped two videos together. So, where were we? So we'll go to hydrogen bonds in week 6. Hydrogen bonds are really important for organic chemistry, as they are the strongest kind of intermolecular force. They're the ones that are important in biochemistry, so holding proteins together. Solubility. And we'll look at some biological chemistry, the chemistry of biological molecules. And as the name suggests, they are within the body, or in life in general. And we will pick apart how organic chemistry, how the body relies on a lot of these organic chemistry principles and how we can apply them. So it's not just learning about concepts and principles there. Testing for chemical characteristics. This will be partly theoretical, partly multimedia showing these reactions. Some of them I won't be able to do here. Where I can, I will do them live in the seminar. Hopefully don't blow up all my computer equipment. I'll get in trouble for that. So chemical reactions, which is kind of the final, or the top end. So we know so much about organic chemistry that we know what happens when we mix one with another, or we add a catalyst, or we add UV light. And we can say, well, when you mix this with this, we get this. That's the top level knowledge for organic chemistry. All this stuff, you're just knowing stuff. Here, you're testing for that stuff, so you know a bit more. Here, you know everything about stuff, so you can then rearrange it and put it back together. Where a lot of people falter. But hopefully by the time we get there, we're very clued up. So, organic chemistry, it's the study of life. Well, sorry, not the study of life, that's biology. The study of the underpinnings of life. So if you look back to the beginning of where life came from, they think that it was down the bottom of the ocean, where all of these hydrothermal vents, and there's lots of carbon and there's lots of hydrogen down there, and the intense heat. Over time, with carbon and sulfur as well, gave rise to what we now know as life. And we can make assumptions about whether life might be on other planets by whether we find any of these what they call building block organic compounds. So biochemistry, study of DNA, the study of proteins, is all underpinned by this organic chemistry. Molecular biology, or the study of genetics and the study of manipulating those genetics to create GMOs. All of its basis, again, is in this organic chemistry. So therapeutic chemistry, or there's a couple of ways you come up with new drugs, or pharmaceutical drugs. We have chemists that just we take one compound that we know is therapeutic, and then we just make loads of different variations of it, chemically. Another way is the biology, or the molecular biology method, which is using living cells. Pharmacology, no, at least one of you guys, I think Margaret, is wanting to do pharmacy, I think. And most of our drugs are organic compounds. They have rings, they have functional groups. And so second semester, or Chem 2, definitely know a couple of you doing Chem 2, is heavy on the organic chemistry. So that's why I'm doing this in this semester at this time. And this will give you a really good grounding, even if you're in grade 10, and there's one grade 10 student. If you can understand this now, then year 11 and 12 should be a breeze for you. So the one thing you'll get sick of me talking about is intermolecular forces. They underpin everything in organic chemistry. And they're not the forces that hold the molecules together. They would be intramolecular forces. But these are the forces that connect two molecules. So They affect the boiling point and the melting point. The stronger two chemicals are bound together, the higher the boiling point. Because when we boil something, what we're doing is taking the molecules, breaking them apart, and then they become a gas. Solubility. So hydrocarbons like petrol and oil aren't soluble in water. And there's loads more. But I won't bore you to death in this first week at all. So, electronegativity. It's not something that's taught particularly well. It's made to be more complicated than it is, and I don't know how they make it complicated. But from the bottom left to the top right of the periodic table, electronegativity increases. So hydrogen is 2.2, and oxygen is 3.4. So there's a significant difference there. Now, you don't need to know the numbers. There's 118 elements, and I'd be really impressed if you could remember all of the electronegativity values. You just have to know that where they sit will determine whether or not there's a significant difference. So hydrogen and oxygen, there is. Carbon and oxygen, there is. Nitrogen and hydrogen, there is a significant difference. So if we look, so I'm going to load my periodic table now. Okay, so let's pretend that you can see my periodic table there. Bottom left to the top right is the increase in electronegativity value. So, dispersion forces. So, we all know that atoms are, neutrally charged. They have a neutral charge. They have no net charge. But that doesn't mean that at all times the electrons going around a nucleus are evenly distributed. And what we end up with is the side where the electrons are is negatively charged, and the other side has a positive charge. And then like a magnet, other atoms line up against it. And we get these really weak intermolecular forces called dispersion forces. So they are present in non-polar solutions. So anything that does not have a polar bond, or anything that does not have a significant electronegativity value difference between the two atoms in a compound will give you a non-polar covalent bond. So if we go all the way back to covalent bonds, ionic bonding is when the metal donates its outer electrons. And if we look at covalent bonding, they share their outer shell. So the outer shell actually goes in the whiteboard. So, come down a little bit. So if we have what have we got? Let's say carbon and carbon. So what happens is carbon shares its outer electrons, and what happens is their outer shell becomes something like that. So the electrons in carbon to carbon are shared evenly between the two. So the 4 electrons that they're each sharing with each other in their outer shell are evenly distributed, or relatively evenly distributed around the outer shell between the 2 carbon atoms. And this is a non-polar bond. There is no negative or positive end of the molecule. Doesn't exist. They're sharing. If we take hydrogen, add water, 2 oxygen molecules, if we take oxygen and we add 2 hydrogen to make water, my bad, the hydrogen becomes positively charged because the oxygen will hog the valence electrons. It won't steal them, but you can assume at any point in time that you will have H plus and O2 minus. Important thing to note, oxygen is in group 6, so it needs 2 electrons to fill its outer shell. And I'll keep coming back to the position of elements on the periodic table. And if you've ever had me rant about the periodic table and how you can tell everything, you'll know that all of this makes sense when you understand the periodic table. Oxygen is in group 6. It needs 8 electrons to make an octet. It binds to hydrogen. It hogs the electrons in the bond. That's why oxygen is often O2 minus. Hydrogen is H plus. So that's how we get a polar bond. Okay. So dispersion forces are between the atoms, so there would be hydrocarbon, something with a hydrocarbon backbone, and I'll explain what that is in a few slides' time. The hydrogen atoms that are on the ends that touch, the dispersion forces act between those two. They're very weak. So dipole, like the case of well, water can be either a dipole or a hydrogen. So polar bond, negatively charged end and a positively charged end. So one of those atoms is going to hog the electrons. So at any point in time, you can safely assume that one end will be positively charged and the other will be negatively charged. So intermolecular attraction is a weak force, even though it's a dipole-dipole force, it's still relatively weak. The covalent bond obviously is really strong. And when we're talking about intermolecular forces, we aren't worried about the bonding between the atoms. It's the bond, it's the attraction. It's not a bond. It's an attraction force. And there's an important distinction to make. So intermolecular attraction is weak in comparison to a covalent or an ionic bond. So hydrogen bonding is the reason that water is water. Without hydrogen bonding, or if hydrogen bonding was ever so slightly different, we wouldn't be here because water wouldn't have its properties. All of the weird and wacky properties of water, the fact that it can exist in 3 different states, the fact that it takes up more volume when it's frozen, so it takes up more volume as a solid than it does a liquid, is because of the hydrogen bonding within the water. So, and I'll put this again on the whiteboard as so we've got we've got 2 water molecules, and then we have another water molecule where the oxygen is at the top. And let's remember that the oxygen is negatively charged, it's O2 minus. And it's come up with 2 positively charged hydrogen. And the more negative the oxygen is, the stronger these bonds will be. So we then have another molecule, 2 molecules of water now bound to another one through hydrogen bonds. And these bonds are really strong because they're still relatively weak, but they are much stronger than the other 2. Than the dipole and dispersion forces. So, hydrogen bonding. Hydrogen binds to oxygen. And it creates, in water it creates like a net. And that's why you end up, when you hit water, it's like hitting a brick wall from a certain height. Whereas other liquids, it's not. So, organic chemistry, yeah, carbon-based compound. Yeah, some people just want to watch the world. So, think to yourself, when you're looking at carbon, it has 4 electrons, 4 valence electrons that are all available for bonding. So it's in period 2. Silicon is also in group 4, but it's in group 3. So, because of this, carbon forms stronger bonds. Now, I will elaborate on this theory in the 5-minute video. But there is a theory out there that says when we get to the other planets, that silicon could theoretically do the same thing as carbon. There could be silicon-based life out there because on a lot of planets, there's not a lot of carbon available in comparison to silicon. And they think that maybe we could have become a silicon-based life on Earth, but there was an abundance of carbon. And again, I'll go into that in the 5-minute video that I'll put out. And I think I'm speaking way too quickly, so I might put out 2 5-minute videos. Okay, so carbon forms single bonds, double bonds, and triple bonds. It's a bit like water. Most things will form one or the other. Oxygen forms double bonds, it's in group 6. Nitrogen is in group 5, forms triple bonds, shares 3 bonding electrons And it can occur between the carbon atoms. So if we look at, I'll do an angle, but my camera is being. There we go. So, keep on the screen. So carbon can form single, double, and triple bonds between itself, or not itself, another carbon atom, or with another molecule. So hydrogen cyanide, its Lewis structure something like that. So carbon and nitrogen form a triple bond, single bond to the hydrogen. We can also have carbon to carbon. So carbon forms a double bond with itself, and then usually it has, so I'm going to jump ahead a little bit. So if we were looking at a hydrocarbon, that's what a basic hydrocarbon looks like. We can alter that, and let's go all the way back to Lewis dot structures. I think all of you have a pretty good grasp on Lewis dot structures. So carbon has an octet because each of these bonds represents 2 bonding electrons. Carbon can make a carbon to carbon bond, and we would drop this. And now you have a completely different molecule. It can also triple bond, so it shares 3 pairs of electrons. And this will form the basis of our naming of these organic compounds when we look at this hydrocarbon backbone. So that's why carbon is special. It can make all these different kinds of bonds with all different kinds, and they are much stronger than other elements in group 6. Sorry, group 4. Group 6 is oxygen. Okay. So hydrocarbon chains, those carbon backbones that we talked about, carbon, 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 and then hydrogen all the way around. They form the basis of all of these organic molecules. And the difference between the organic molecules and the different names, anes, enes, ines, oleic acids, fatty acids, all depends on what that functional group is, whether it's got oxygen, or it has OH minus, whether it's an ester, whether it's an aldehyde, so on and so forth. So when we increase the size of the bond, so from a single to a double to a triple, we significantly increase the amount of energy that's required to break the bond, but it also increases the energy required to, the energy that we get from burning the bond. So hydrocarbons is the technical name for most of our fuel, whether it be gas, butane, propane, methane, ethane, octane, the stuff that they put into the fuel and charge outrageous prices when they add a little tiny bit more, is all to do with these bond energies. The amount of energy that's present in the bond So when we eat food, fatty acids contain 9 calories per gram. That's all to do with the amount of energy that's stored within the chemical bonds. Carbohydrates and proteins only contain 4 calories per gram. Now, all that is because there's more chemical energy stored in the bonds in fats than there are in other ways. Interestingly, alcohol is 9 calories per gram. So we start talking about low carb beers. It seems a little bit silly when you're looking at hundreds and hundreds of calories in alcohol. Anyway, yeah, so fossil fuels, the higher the energy content, the more energy you get out, but also the more energy you need to put in to break the bond initially. Obviously, a triple bond has the most. Sorry. So, hydrocarbon backbone. There's a reason why I don't put many words on the slides. I just find people read the words and they don't actually take in what I'm saying. And then if I put words on the slide, if I put words on the slide, do it there, do it. My phones came up and I got distracted, like a child. So the hydrocarbon, 2 carbon atoms, hydrogen all the way around. And that is what we call the saturated hydrocarbon. And these form the basis of all of the organic compounds. So we can have, apologies, nitrogen, hydrogen, oxygen. These all form the basis of our functional groups. Functional groups are different atomic arrangements or molecular arrangements that give rise to a common set of chemical characteristics, is how we describe functional groups. And depending on how they're laid out, influences their intermolecular forces. Sorry, brain fade there. Influence their intermolecular forces, which again influences everything about. So 2 molecules can have the same size, or 3 or 4 can have the same size. So ethane is a gas that we use for cooking. It's the same size as ethanol, which is grain alcohol, or alcohol that we drink. We then have ethanoic acid, which is in vinegar. And ethane has a boiling point of minus 89 degrees Celsius, I think. And ethanol has a boiling point of 76. Ethanoic acid, which has a different functional group, has a boiling point of 116 degrees. I might be off by a degree or 2, but you get the point. These functional groups, though they may be insignificant, they will dramatically change the properties of the organic compound. So in saying that, it doesn't have to be a different molecule. It can simply be a double bond or a triple bond between the carbon atoms, somewhere in the chain. It does not have to be a whole another set of elements or compounds attached to it. It can just be a double bond, because that gives rise to a new set of common characteristics or a functional group. So, but when we replace hydrogen with anything, it becomes one of these functional groups. So, ethanol, everybody knows what ethanol is. I think maybe one or two students who aren't over 18 in this group, everybody knows what everyone knows what ethanol is. And all we do is replace the hydroxyl group, replace the hydrogen atom with a hydroxyl group, or OH. So we go from ethane to ethanol. If it ends in ol, it's an alcohol. If it ends in ane or ine, it's a hydrocarbon. So we've taken a gas we use for cooking. We've really just added an oxygen onto that group at the top right there. And suddenly we have a completely different molecule. Same size, maybe ever so slightly bigger, but not anything we could ever measure. Same size, all of a sudden it has a massive effect on people when they intake. Ethane is used for burning in gas cooking. So we then take ethanol or ethane and we add a carboxyl functional group. So that goes on to the end. So OH and then a double bond between the carbon and oxygen. This gives carboxylic acids like ethanoic acid. There's loads of different ones. They all have really strong intermolecular forces, so their boiling point is really high, and they can dissolve into water. But if I took ethane and I tried to dissolve it in water, it wouldn't happen. So all we've done is change the functional group. It's the same molecule, the same molecular size, and all of a sudden we've completely changed what the molecule is. And if you understand what these changes are, then organic chem isn't as scary. And that's what I'll hope to get across, is that there are a set of simple rules that if you follow them, everything should make sense. Should. So this is where I get a little bit weird, and we'll go through this in one of the later lectures, but they don't have to be all together. So the halogens in group 7 are really, really reactive. Fluorine is really reactive. And then what we call a halo alkane. Don't worry about the name, it looks really complicated. I will take you through that step by step so that it's nice and easy. And every week builds on the previous week. This week is quite light, it's an intro. Everyone's busy. I know people have exams, we've got school holidays coming up. But it will build and build and build until we get to the top. But by the time we're at the really juicy, hard stuff, it should be relatively easy for you. So, classifying organic compounds. We classify the compounds based on their functional group. And in this time, we'll go through all 12. I will go through which ones to remember the most, which one you're most likely to be tested on. But it's quite a task to remember all, but we'll get through it. Okay, that's the end. And I spoke for longer than I thought I would. I didn't think I would go as slow as that, but that's given me something to work on and how much I can get through in an hour. So thank you for listening. I will put this video together and I'll send out the 2 and 5 minute videos which I'll film on my iPhone, it's apparently in 4K now. And I'll send out the tutorial sheets as well. So thank you for coming and enjoy the rest of your week.